this video, we are going to briefly study something called phase. If we look at this oscillating mass spring system, we notice that it passes through a series of different positions. So first, it starts all the way out here, and it's something like this. After 1/4 of a period, it's like this. That's where it is at, when the amount of time has passed. This is where it is when no time has passed. And this is where it is after 1/4 of a period has passed. After another quarter, so when a total of 1/2 period has passed, it's right here at the edge, the left edge. If we let another quarter pass, it gets back to the center position. And if we let an entire period pass, it's returned to the outer edge, and it's about to start the succession again. It's about to start moving to the left again. So what do we call these distinct stages? Make sure I'm by the mic. What do we call these distinct stages? What do we name them, and how do we quantify them? Right? By the way, this one is different from this one because right here the system is moving left, and here the system is moving right. So that makes them different. They're distinct. But the point is, what do we name them? We can't just call them stage. That's not very scientific. We don't sound very smart when we do that. Instead, we call these different phases. And phases just means the stage, or what portion or fraction of the way through a full cycle is the object. So if we look at these distinct phases I've drawn, the way we measure phase is with radians or degrees. So I'm going to move this up, and I'm going to put phase here. Before any time has passed, at the very beginning of the cycle, we say that the phase is 0 degrees or 0 radian. 1/4 of the way through the cycle, let's go to the end. At the end, when we've completed a full cycle, we are back to 0, except we don't call it 0. We say we have completed 360 degrees. The phase is 360 degrees, or 2 pi radian. So let's try that again. 360 degrees. Halfway through the cycle, when the time that has passed is half a period, the phase is 180 degrees, or pi radian. And 1/4 of the way through, it's 90 degrees, or pi over 2 radian. And 3/4 of the way through a cycle, when 3/4 of a period has passed, what stage are we at? What stage of the cycle are we at? The stage, or the phase, is 270 degrees, or 3 pi over 4 radian. Nope, hang on, that's not right. Not 3 pi over 4. It's 3 pi over 2, excuse me. Pi over 2 radian. And what we use in IB physics typically is radians, not degrees, to express the phase, the stage. So there are 2 ways to measure how quickly the cycles occur. One is using the plain old frequency f, which is just counting cycles, how many cycles occur per unit time per second. The other way is angular frequency. And angular frequency, which gets the variable omega, lowercase omega, which is a fancy W. And let me make a better omega. Kind of looks like that. Angular frequency is not how many cycles occur per second, it's how much phase occurs per second. How much phase does the system pass through per unit time? That's what angular frequency is. Now, in one complete cycle, we pass through 2 pi radians of phase. So there's a special relationship between angular frequency and regular frequency. Here it is. This is a special relationship. Angular frequency equals 2 pi times the regular frequency. And this relationship we could write in terms of period of oscillation, like that. These are 2 very important equations which we will use repeatedly in this unit. So a question for us is why is this 2 pi appearing? And the answer is actually simple when we look at this form of the equation. Angular frequency is how much phase occurs per second. And in one complete period, we pass through 2 pi radian of phase. So the angular frequency can be calculated using this equation, 2 pi radian per second. And we don't write this in, but really the numerator is 2 pi radian. What we do instead of writing in radian in the numerator is the unit for angular frequency is simply radians per second, or in IB language, radians times second to the -1. So after we solve a problem, if we are given that the period of oscillation is, let's make it easy. The period of oscillation is 0.5 seconds. Find the angular frequency. You would say, okay, the angular frequency is 2 pi over the period, 0.5 seconds. And of course, we could write this as 4 pi, and then we would just tack on radians per second, or radians second to the -1.